Hi everyone, so in this video we are going to make CFD analysis for my aircraft. Okay, we want to grab a mesh and then Fluent, and let's start. Import your geometry. My geometry is a SolidWorks part. It can work on Ansys, no problem. Now edit in Design Modeler. We are going to make our CFD analysis for variable angle of attack and variable side slip angle and also variable velocity. So we imported our aircraft. Let's explode this part. Grab a boolean, unite all these bodies, generate. I made these bodies separately intentionally because for another videos we are going to make CFD analysis for variable elevator and aileron deflection angles. Now we are going to make a sketch on the XY plane, of course. We are going to make our domain. Make it big so the walls won't affect our airflow. This is good. Yep. Now extrude. Add a frozen symmetric. Make it 5. Okay. Generate. There is a problem. What's our problem? Let's see the problem. I generate. Oh, no. Let's edit our selection. I didn't select the sketch. Now it's good. Do you see that? Alright. Now insert a new sketch. Edit this sketch. Make a circle. This is going to be our body of influence. Here is good. Okay. Now also extrude it. Add frozen. Symmetric, of course. Make it 0.6. 0.7. Okay. It's going to be only around the aircraft because at this region the mesh is going to be highly dense. Now we are going to make our rotation or the angle of attack and the side slip angle. Rotate the body inside the both bodies. Rotate it about Z-axis or pitching axis. My maximum angle of attack is going to be 24, and also you have to make a parameterization. Okay, this is going to tell Ansys that this value is going to change. So it's alpha. Generate. Okay. Now we are going to make beta. Apply. Beta is going to be around the y-axis, and it's going to be, the maximum is going to be 20. Okay. Now this is beta. Generate. By the way, this is positive beta, and this is negative beta. Let me show you. This is negative beta. This is positive. Okay. Now we are almost done. We are going to make a boolean subtract from the domain. We are going to subtract the aircraft. Now generate. Okay. Now we have two bodies. One of them is the domain. It's going to be the domain. And this is going to be our body of influence. You can not make the body of influence if you want, but I want to make it. It's your choice. It is for meshing purpose. Now here we are done, but we must make the name selection before we go. Now this is going to be our inlet. Those are going to be our walls. And the outlet. Now we are done. Not really. We need also to do one more thing. Hide these surfaces. Hide also the sketches. Hide this body. Now we have these surfaces of the aircraft. Click on box select. Now make a name selection. This is our aircraft. Done. Bring back everything. You can press Shift F9 and Shift F8 for showing the hidden surfaces and bodies. Okay, we can start meshing. First of all, insert sizing, select here body and select your domain. We are going to make a body of influence. So this is our body of influence. Make it 0.75. Now insert another sizing, select edges, select this edge and this edge and this edge, make a number of division and make it 100. Also make bias, make it 35, or you can use whatever you want. Okay, the meshing is going to be your preferences. Choose whatever you want. Now I'm going to insert another sizing and select these edges. Make element sizing 0.02 and bias, of course. Okay. Now insert another sizing. Choose these edges. Make it 0.02. Do you see that? Do you see it? Okay, now we are going to insert a face meshing. Choose these faces, the outer faces, and here it's 0.7. Make it 0.3. Generate. Let's see our mesh. It's going to be done in a minute. Do you see that? Done. I am not focusing on the mesh. You can make better, okay? But it's enough for me. If you make higher dense mesh, then I think these faces are highly dense. I'm gonna make it bigger, 0.5. This is better. Now we are done. Get out of here. Update upstream components. Do you see this section? This is our design points. We are going to study these design points. We're going to make a lot of design points. So let's keep going. Edit. Double precise. Here you can choose it, or it depends on your computer. If you have 8 cores, you can select 8. If you have 4, you can select 4. It's your choice and your computer. Okay, let's start. For my model, I'm not going to use the energy because my higher velocity is going to be 50 meter per second, and the Mach number is going to be 0.15, and for that we don't need the energy, okay, because it's incompressible. The viscosity, you can choose whatever you want. You can use standard SST, K epsilon, I don't know, use whatever you want. Now we are going to see the boundary, okay. The inlet velocity, you can make it parameter, but I'm going to use for each velocity I'm going to use a separate file, okay. Now for my 50 meter per second velocity, I'm going to use this file. This is my inlet. Internal, we don't have any business here. This is the outlet pressure, okay, and this is the walls, okay. We don't have anything to do with this. We only need the inlet velocity. Now here, this is the reference values. For example, if you are going to take the lift coefficient, then you are going to compute from inlet or wherever you want to compute from, okay. But these values are going to be used for the coefficients, okay. For my aircraft, the area, okay, is going to be 0.479, and the chord is going to be 0.318, okay. This is the mean aerodynamic chord. I calculated from another program and another thing. So this, you want to be careful with this, because this is what the forces and moments are normalized for, okay. Now here you have the methods. Again, you don't have to change anything, but for me I'm going to choose this green Gauss cell based, okay. You don't have any business here. Now the residuals, the continuity equation, if you make this number less and less, you are going to have better values, okay. The values are going to be more accurate. So I'm going to add 1 0. Why didn't I add more zeros? Because I don't have a lot of time, okay. This is going to take a lot of time, as we said before. Now we are going to here to calculate the forces that we need, okay. So let's start. This is going to be our X force. At first, let's display our aircraft. This is all we need. By the way, the forces I'm gonna take, it's in the wind frame. So forces, the X force on the aircraft, and also create output parameter, so we can see it from out of this window. This is on the -1. This is what with respect to what frame you are going to take your forces. So for this frame, I want to take the forces not in this frame but another frame. So this is why I take -1. I make it -1 for the X value. So it's going to be in the opposite of this X. If this X like this, I'm going to take Do you see X like this? I'm going to take with respect to the reversed frame of this. Now let's see the side force, which is Y. On the aircraft, this is going to be 0, and the side force is going to be in the minus Z direction, and also create output parameter. Now new, if you want to see why we are clicking on the create output parameter, let's see it. Click here. Do you see that? This is X and Y. So when we click on the create output parameter, it's displaying the forces here. Now let's get back to here. New force on the Z direction, and it's going to be in the minus Y. Create output. Okay. No. Edit. Create output. Okay. Now we are going to calculate the moment. By the way, don't click on the moment coefficient unless you want the moment coefficient. So be careful. This is going to be the rolling moment coefficient on the minus X direction. Create an output parameter. Okay, we are done here. New moment, the pitching moment here. It's going to be the pitching moment on the minus Z direction. By the way, here you can for the moment you need to specify the origin of the moment you are talking about. Okay, so for me it's going to be at the center of gravity, and in this particular geometry the aircraft is at the center of gravity. Okay, the origin is at the center of gravity of the aircraft. -1, create output. Okay, a new one for the yawing moment, not coefficient. This is the yawing moment. This is 0, -1. Create output. Also, we are going to take the lift coefficient of the aircraft. Now we are done. Create a new surface to display the values, the pressure and whatever. Create, close. Okay. Now at first we're going to initialize our model. You know, I'm going to initialize it from the inlet, absolute initialize. Now here I'm going to add the pressure on the aircraft and the plane. Okay, we are going to display the values of the pressure and of the pressure also only. New one for the velocity on the aircraft and the, not inlet, the plane. Close. This is before the calculation. Do you see that? This is going to be 0. Why? Because we have walls here. Now here what wait a minute. Here what we said, we are taking the static pressure. Now I'm going to take the total pressure. Total pressure here on the aircraft and the plane. Do you see that? This is because our beta is maximum and it's 20. Okay, this angle is 20. So also we are going to use baselines starting from the inlet and from the aircraft. Okay, and it's going to be colored depending on its velocity. So, and here, from here you can lower the density of the baselines. I always make it 1. You cannot make it 1. It's up to you. Now we are going to see the baselines. By the way, this is before we calculated anything. So this is the initial condition. Did you see it? We initialized the problem, so we didn't calculate anything yet. Now run the calculation. Make it 250. Calculate and wait. This is the lift coefficient. Do you see? Each iteration, it's improving. This is the yawing moment, the pitching moment, the rolling moment, the not the body force, but the wind frame, Z force, Y force, X force. Then after we collect all the data, we are going to convert it from the wind frame to the body frame. Okay. The lift coefficient looks good. Yeah, it's reasonable. By the way, this analysis is only for to see when it's going to converge. Okay, then we are going to make the number of iteration lower. Why? So it doesn't take a lot of time. And by the way, all the values are close to real life. It's not precise. So it's accurate but not precise. Do you see it converged? Yeah. Here it also converged. The moment, of course, it converged. The rolling moment, it didn't converge yet. Everything is converging, so it's good. If it's not converging, you might wanna change your model, or your mesh is not good enough. So it's very important to see the conversion. Why? Because if you are not seeing the conversion situation, it means your values are not reliable. Okay. Yeah, it's good enough. Now we want to stop it because do you see it converged? Yeah, it is converged. So now when it's converged, we can know that this number of iteration is enough for us. So we can make it 70 and initialize the model from the inlet, initialize, or also before initialization, let me show you what we calculated. Let's display it. Do you see that? Do you see? The region here is bigger. Let's see if we have symmetry or we don't have. Actually, we should not have symmetric. Why? Because we have angle of side slip. Do you see here? It's bigger than here, the blue area. Now let's see from the lower surface. Nothing is obvious, but this is more obvious. Do you see that? This is the total pressure changing. Yeah, I think it's good enough. Now let's see another thing. This is the velocity. Of course, the velocity at the walls is going to be 0. Why? Because we have no slip boundary condition. Okay. So why we are seeing this blue area? Because this blue area has less velocity than this green area. Now this is the velocity. Let's see another thing. Static pressure. You can visualize a lot of things, but those are enough for me. Now let's see the bus lines, because they are the most important. Not the most important, but the most satisfying visualization. Display it. It's going to take some time. Do you see that? Do you see that? So the airstream is coming from the inlet and moving like this. So we don't have symmetric, which is true. Now we might wanna delete everything because we are satisfied. Okay, we are satisfied with everything. Everything looks good. Delete everything. Delete the past lines. Now we deleted everything. Why? Because we don't want it to calculate it, these results every time, every design point. Okay, because every design point, this is all the thing we need. Okay, we don't need anything else. Initialize the model from the inlet. Initialize. Okay, now run calculation. it started. We are almost done, but there is something we are going to make before we end this video. At the end, it's going to converge because we already saw the plots. It's just repeating it. You don't wanna go with high iterations because it's going to take a lot of time. This is enough for you. I already did this analysis, but I'm repeating it to show you how. I'm going to show you the results. So we can stop at here. You can continue, of course, you should continue, but because I already did this. Now, okay. This means that we stopped the analysis without finishing it. Okay, it doesn't matter, but you should finish it. Okay, now we are going to go to Excel. We are going to make design points. Okay, so we said that our analysis from -24 to 24, it's increasing by 3. This plus 3. Okay, now this for what? To 24. Okay, then we are going to copy it and paste for each angle of side slip. Now our first angle of side slip is going to be 0, of course. Then it's going to be 5. Then we are going like this until we reach 20. Okay, so it's 0, 0, 5, 10, 15, and 20. This is the angle of side slip that I am making the analysis for. Now don't get out of here yet. Copy this and paste it in the Ansys program. Paste. Okay. Now, if you want to make analysis for the design points, don't click on all of them at one time. Okay, make analysis for each 10 design point. Update. Okay, now it's going to be update it automatically. So it's going to go in this design point, it's going to make analysis for this design point, it's going to calculate the forces and moments for this design point, and after it finished, it's going to go automatically for the next design point, which is -21, 0. Okay, don't let it calculate for all of the design point. Sometimes Ansys crashes, not crashes, but stops. Okay, it doesn't go any further, so you need to abort. If you said you need to keep your eye on it. Okay, so if you said that it took a lot of time for the same design point, don't let it continue. Abort. Okay, and continue from the last design point, like this. Clear the messages. Now do you see at the end, let's say that we make from the first design point to the design point number 11. Okay, then we saw that Ansys didn't continue, or it's taking a lot of time. So make abort the process. It's going to be the last design point available design point is going to be 10. So start from 11. Of course, before you start, save your project. Okay, now we are done. I don't want to save this project because I already have it. I'm gonna show you. It is opening. Now go to the parameter set. Do you see? I calculated all these design points. These design points are good, are working, but after I reached this design point, I changed the number of iterations because it was making a lot of iterations, so I changed it. Okay, it was 80 iteration, then I made it 60. Now I reached this design point, so I'm going to start from here until, let's say, here, update selected design point, and we are done. Okay, after we did this, we are going to take this data and add it to Excel. Okay, I already have one. Let me show you. Do you see this? This is a lot of data. Okay, but after I did all this analysis, I realized that I made only 20 iterations, so it's bad. So I collected all this data, then I converted from wind frame to body frame, then I took the coefficient from it. Okay, do you see that? This is a lot of data. It took me a lot of time. This is for the elevators changing. This is for the aileron change, deflection, aileron deflection. This is for the body angular velocity. Alpha dot I didn't made it yet, but I am going to. Okay, we are done.